Hi, Mrs. Stanley here. Let's talk about the derivatives of inverse functions. First of all, this is topic 3.3, differentiating inverse functions. We'll just read this quick paragraph to remind ourselves what is an inverse function. Recall from previous courses that a function y equals f of x, that is 1 to 1, will pass the horizontal line test and will therefore have a unique inverse function y equals f inverse of x. We often say that the inverse function undoes the original function f of x. This can be seen in the test to prove two functions are inverses of each other, since the composition of the two functions produces the identity function. So what this states right here is just that if I were to plug in f inverse of x in for x in the function of f, the answer I would get would be x. And the same thing would happen if I had the f inverse and I plugged in f of x for the value of x. So that's just an interesting piece of information to keep in mind. Now let's look at this definition of an inverse. I feel like it's a repeat of what we just said, but let's just do it. A function g is the inverse function of the function f if f of g of x equals x for each x in the domain of g, and g of f of x equals x for each x in the domain of f. The function g of x is denoted by f of negative 1x. So what happened here is that they stated this originally using f and f inverse of x, and coming down here they're using f and g. Okay, and so g of x is representing the f inverse of x. So it's a restatement of that same sentence, just using f and g instead of f and f inverse. Now let's look at the reflective property of inverse functions. The graph of f contains the point AB if and only if the graph of f inverse contains the point BA. Notice the difference, AB, BA. If you remember back all the way in Algebra 1 when you learned inverse functions, the first thing we notice is that A and B are, the y and x and y are switched. In this case we're using A and B. In Algebra 1 we generally just stick with x and y. So coming down here, this first thing we're going to do is going to seem really simple. Don't overthink it. Use the reflexive property of inverse functions and the function values for f of x and g of x in the table at right to complete the table of values for their respective inverse functions, f inverse x and g inverse of x. Then use them to answer each of the questions below. So right here we have a table with x and f of x. In order to do it's not my highlighter anymore. To do f inverse of x, we're just going to take these values for x and f of x and flip them. It's going to be 2 and 3. And then for the next one, it's going to become negative 1 and 1. And then for the last one, it's going to become 4 and negative 1. And now I'm going to stop making these marks and we're just going to do g. Remember, g is here and x is here. So we're flipping these two. We're switching them. So we're going to have negative 1, 3, 0, 1, and 3, negative 1. That's what it means to be the inverse. The x's and y's exchange places with each other. So coming down here, use the tables above to evaluate each of the following expressions below. So we've got some compositions of functions, but they're just the functions and the inverse functions. So let's look at this first one, f of g inverse of 0. So we've got g inverse of 0. That's the first thing we need to know. What is g inverse of 0? This is our table for g inverse. When x is 0, we get 1. So what I'm finding now is f of 1, which is what? I just go back to my original function up here. F of 1 is negative 1. So my final answer is negative 1. So I could rewrite it, f of g inverse of 0 equals negative 1. And that's my answer. Let's try it again. D, this time the inverse is the outside function. So I've got the f inverse of f of negative 1. So the first thing I need to find is f of negative 1. Go back to the original table. F of negative 1 is 4. So now I need f inverse of 4, and that's right here in this f inverse of 1. I think I said, yeah, don't confuse f of negative 1, which would be right here. This is f of negative 1. This one is f inverse of 1. It's easy to kind of mix them up in your language, so be careful with that. So continuing on, f inverse of 4 is negative 1. So again, we could rewrite it. F inverse of f of negative 1 equals negative 1. We got the same answer. Now this time we have f inverse of g inverse of negative 1. So first thing to do, g inverse of -1 equals 3. So now I've got the f inverse of 3. Oh, that's not in our table. Look right here. None of these are a 3. Well, don't over stress about it. All that means is we can write our answer right here. It is not defined. Oh, I need a pen, not a highlighter. So we've got not defined. F inverse of 3 is not defined. Therefore, F inverse of g inverse of -1 is not defined. If you can't find one piece of it, then you just can't get the answer, and that's okay. All right, going on, g inverse of f inverse of 4. So first I need f inverse of 4, which is -1. And so then I need the g inverse of -1, which is 3. So g inverse of f inverse of 4 equals 3. Now, if that felt really fast, please keep in mind that we weren't really doing any calculus. We were just doing inverse functions and composition of inverse functions. So that was a lot of review. Let's skip down now. The existence of an inverse function. Here's the two statements. Number one, a function has an inverse function if and only if it is 1-to-1. Remember, 1-to-1 means what we talked about there back at the beginning. You can go back and review it if you need to. If f is strictly monotonic on its entire domain, okay, monotonic is defined right here, either increasing or decreasing on its entire domain. So it never has like an inflection point or a maximum or a minimum where it reverses from being or switches from being increasing to decreasing, etc. It's always increasing or always decreasing on the entire domain. So if f is strictly monotonic on its entire domain, then it is 1-to-1 and therefore has an inverse function. That's a good thing to know, just to keep in mind for just those random times it becomes useful. So, next thing, the relationship between a composite function and its inverse is stated below. If you use the chain rule and differentiate both sides, you can find a formula for the derivative of an inverse. So what we're going to do is we're going to take this composition right here and figure out what is the derivative of an inverse. So we're going to apply the chain rule because it's a composition, and let's do that. We're using implicit differentiation though, because notice it says equals x. So we've got x's on both sides of the equal. We're going to use implicit differentiation. So number one, just to keep notation simple, let g of x equal f inverse of x. And so I can rewrite this to be f of g of x equals x. That's just going to be a little bit easier than having to keep writing f and f inverse. And then for number two, step two, it's not really number two, but second step in the problem, we are going to do implicit differentiation. So d dx of f of g of x equals d dx of x. So take the derivative of both sides with respect to x. So f of g of x is going to be chain rule. F prime, the derivative of the outside, leave the inside alone, times the derivative of the inside. Equals, what's the derivative of x? It's just 1. Okay, so look at this. F prime of g of x times g prime of x. This is just the chain rule. But remember, we're trying to solve for the derivative. So g prime of x is going to equal 1 over f prime of g of x, right? Now let's go back and plug in our notation. Remember right here we said g of x equals f inverse of x. So let's rewrite this final answer that we got here, the derivative. We found g prime of x. That's what we were looking for. Because what does that tell us? F inverse of x prime, the derivative of f inverse of x, equals 1 over f prime of f inverse of x. Okay? Think about that for a moment. The original function is right here, f of f inverse of x. And I'm sorry, this looks kind of like a 1. So I want to change it. That's the f prime notation. And even right here, it looks like a little bit of a 1. This is the prime notation. We're taking the derivative of the inverse, f inverse of x. There's a couple ways you can write that. Let me change my pen color and just tell you real quick. You might see it like this, prime of x, f inverse prime of x, or you might see what I already did down here, f inverse of x, oops, with a box notation with the prime outside. There's different ways that this is written. Just be careful to watch for the prime and be careful to make sure that you write it yourself in one format or another. Sometimes what happens is that it works best if you just pick one and stick with that, because then you'll always do it instead of mess up. And you know, we don't want those random little mistakes. So perhaps one thing that's noticing, what do you think of if you see, for example, I can't get my pen to work. If you have x and 1 over x, they're not equal. I shouldn't use an equal sign. What do you notice when you switch from x to 1 over x? Is there a specific vocabulary word that comes to your mind? Hopefully you think of the word reciprocal, and notice that these two pieces of information, f inverse of x prime equals 1 over, it's like the derivative of the inverse is the reciprocal of the derivative of the original function, right? Let's look at the next one. It'll start to come together. The words sometimes make it seem more confusing. So here we go. Given f of x equals 4x minus 3 and f prime of 2 equals 4, find the value of f inverse of 5 prime. So first of all, you might be like, wait, I don't even know what f inverse is. That's okay. Let's just take it step by step and look at what we do know. We know, for example, that if what we're looking for is the f inverse of 5 prime, we know that if 5 is the x value on the inverse, on f inverse, it is the y value on f of x. And I should have written right here f prime of x. Let me fix it. I meant f inverse of x. Right here I changed it. So if 5 is the x value on f prime of x, it is f inverse of x. It is the y value on f of x. See, we can use our original function f of x right here and set it equal to 5, because it's now the y value I can solve. So if 4x equals 8, then x equals 2. So that means f of 2 equals 5, right? That's good information to know. So what does that tell us? If f of 2 equals 5, f prime of 5 equals 2. So we know this much so far. So let's keep going now. What about, we want to know the derivative. Now remember this formula that we just found right up here. This, okay, let's write that out. F inverse, this is going to be number 3, yep. F inverse of 5 prime is going to equal 1 over f prime of f inverse of 5. Okay, so what does that mean? All right, we already said that f inverse of 5 equals 2, right? We said it right here. F inverse of 5 equals 2. Oh, look at that. I wrote f prime. I meant f inverse. Let me fix it. I got to warn you, just like what's happening to me, that prime and inverse goes back and forth, and it's so easy to make it look confusing because they even look alike, and we use the prime so much in calculus, and then now we're throwing in the inverse. So just be cautious and double check yourself, okay? So we know that the f inverse of 5 equals 2. So right here, I can change this to 1 over f prime of 2. Now, what's the good news? I can get f prime, right? Think about it. We can take the slope, the derivative of this function. So f prime of x, this is going to be number 4. F prime of x equals 4, because remember they told us it right here at the beginning. F prime of, oh, I'm sorry. Two different things. We know that f prime of 2 equals 4, so I can erase this part. F prime of 2 equals 4. If we took the derivative of the function f prime of x would equal 4 because this is a linear function, right? It has a steady slope. It's always going to be 4. So f prime of 2 equals 4. So this right here equals 1 over 4. And that means that our final answer for f prime, f inverse of 5 prime derivative equals 1 over 4. That's our final answer. I feel like we didn't necessarily need to write this part out because they gave it to us in the function, in the question. So the inverse of f at 5, taking the derivative, is 1/4. Notice the derivative of the inverse and the derivative of the function are reciprocals. So for example, here and here, these are reciprocals. All right, let's go to the next page. Okay, to find the derivative of an inverse function. So this is just basically breaking down the steps that you would want to go through. Let f and g be inverse functions. This is the whole truth statement that we already saw at the beginning, is like definition of inverse functions, where f of a equals b and g of b equals a. Notice the a and b, it's like switching the x and y. To find g prime of b for a point a, b on f of x, what do you need to do? You need to find f prime of x. If you are only given b, set it equal. That's what we did on the last problem. Then find f prime of a. This is all steps. Notice this key important fact right here. Inverse functions have reciprocal slopes at corresponding points. What it means by corresponding points is the 2 points like a, b, b, a. Those are corresponding points. You can even see it right here in the note. These are reciprocals. So let's come down and look here at the next problem. Okay, looking at this one, it says find g prime of -1 where g of x is the inverse of x. So first we just need to fill in the table. G is the inverse, so you could make a note right here that this is f inverse of x. We're going to write the 2 points. They didn't give us a column for x and y. They just gave us one column, and so we're just going to write in the points for g. So looking here, if this is 2 and 5, then the inverse is going to be switched 5 and 2. And then here we've got 3 and -1, so it's going to be switched -1, 3. And then -1, 4 is going to become 4, -1. So all we've done is written down the points for the inverse function. Now what do we know about g prime of x? Remember what we said right here. We highlighted it, right? What did we say? The inverses have reciprocal slopes. So f prime, remember f prime, the derivative, is the slope of the tangent line. So it's giving us the slope at that specific point. Well, we said the slopes are reciprocals. So if this slope is 0, then what's going to be the reciprocal? The reciprocal would be 1 over 0. Well, that's not going to work. So on this one, we're going to write does not exist, right? On the next one, the slope is -4, so it's going to be -1 over 4. And on the last one, 6 is going to be 1 over 6. Each of those for g prime of x is going to be the reciprocal of f prime of x. Okay, think about that. G prime of x equals 1 over f prime of x. Okay, so in the statement it said find g prime of -1, and that's going to be, you could look at it two ways. It's going to be 1 over f prime of -1, which we can look in our table for f prime when x is -1 is 6, right? So it would be that g prime of -1 equals 1 over 6. But look, when we filled in the table, we already got that, because g prime, when x is -1, we already said it's 1/6, right? We put it right here. So we already knew the answer. By filling out the table, we got that. So we're good. It's 1/6. Let's keep going. Now in this next question, it's sort of like an FRQ, but we're going to do our best to show our work and write it out. There may be a little bit of ambiguity, and right now we're just learning about inverses, so let's not overstress, but do our best to give as much information as we can. So let's look at what they ask us. Let g be the inverse of f. Calculate g prime of -9 for f of x equals 4x cubed plus 5x. So g is the inverse, right? So we know that g prime is the inverse. and we're looking for g prime of negative 9. Well, first we can make a note that g prime of negative 9 is going to be 1 over f prime of negative 9, right? Let me recorrect that. Not f prime of negative 9. It's going to be f prime of g of negative 9, right? Because remember, it's the reciprocal. Using our formula, going back right here, f prime, right here, 1 over f prime of the f inverse of x. So it's going to be 1 over f prime of g of negative 9. So let's go ahead and get started. We know that if g prime is negative 9, so number 1, g prime is negative 9, that means back up a moment, not f, that 9 is the y value, right? G prime, that's a negative 9. Negative 9 is the x value for the inverse. So then that means the x value for g, it is the y value for f, right? And that shouldn't be g prime. It should just be f, but whatever. So we're going to set our function 4x cubed plus 5x equals negative 9. Now, obviously, this is not an easily factorable function. So we set it equal to 0, and remember in pre-cal we learned how to find possible zeros. We look at p over q, so it'd be like 9 over 4, the factors of 9, or the factors of 9 divided by 4. So we could look at like possible zeros. Remember, we list them out. We could have plus or minus 1, plus or minus 3, plus or minus 9, because those are the factors of 9. And then we need the factors of 9 over 4, which would make a bunch of fractions. So we'll just start with these. I'm going to use synthetic division. I'm going to start with 1 and just see if I can find the 0. Oops, I skipped the x squared. It's going to be 0, 5, 9. Let's see, 1, bring down the 4, 1 times 4. 4 times 1 is 4. This is 9. 9 times 1 is 9. This is 18. I did not get 0, so that didn't work. So now we will do negative 1. 4, 0, 5, 9. Bring down the 4. Negative 4 times negative 1 is just 4. 4 times negative, no, sorry, that's negative 4 times negative 1 is 4. 5 plus 4 is 9, times negative 1 is negative 9, and I get 0. Yay! So negative 1 is one of the zeros, right? I know that f of negative 1 equals negative 9. Now that I know that the f of negative 1 equals negative 9, I can use the original function and the fact that their slopes are reciprocals. If I can find f prime of negative 1, then I would have my answer, right? So let's look at this. Number 2 is going to be, take f prime of x, just take the derivative. 4x cubed is going to be 12x squared. The derivative of 5x is just going to be 5. Now, if I do f prime of negative 1, negative 1 squared is just 1 times 12 plus 5 is 17. So the f prime of negative 1 equals 17. That means that f prime of negative 1 is 17. I can use that based on the rule that g prime of negative 1 equals 1 over f prime of 1 over f prime of g of negative 9. We have from the rules that f of negative 9, the inverses are equal. Remember that thing at the beginning that was like g of f of x equals f of g of x? That's what we're using here. So we know that because f prime of negative 1 equals 17, g prime of negative 1 equals 1 over 17. Because these are reciprocals. And I apologize, I meant to write g of -9. Remember, if for f, this is the x and this is the y. For g, it would be switched, right? Now, this part of the lesson, I feel like in some ways I want to skip it, but it's good information. This is more like review. We're suddenly kind of going to start moving away, and I'm sorry, that's not true. I'm talking about this one, the next step, derivatives of other bases. So example number 5, we're still on the same topic, but we actually have a calculator image, which means a calculator will be helpful in this problem. And the other thing, you'll see this note right here, there are questions where you need to use a calculator to find approximations accurate to 3 decimal places. So just to be clear, you can truncate, which means just cut off your decimal at 3 places, or you can round. Don't use the repeated bar thing. If it's 0.66666, then just put 0.666, or you can put 0.666 or 0.667. You don't have to round it. You can truncate it. So here we go. If f of x equals 4x to the 7th minus x squared plus x minus 5, find f inverse prime of 3 accurate to 3 decimal places. And it just gives you steps here. Solve f of x equals 3. This will give you x equals a. So solve f of x equals 3. That means set this whole thing equal to 3. So I've got 4x to the 7 minus x squared plus x minus 5 equals 3. We want to get that equal to 0. So we got to have minus 8 equals 0. Now this is where your calculator can come in very handy. Unfortunately, I don't think I can record. Let me see if I can. I think I could, but it will make our video even longer. So let me just tell you what to do. I'll write over on the side in a different color, and then you can go back. So first thing to do is enter the equation in y equals button. So push your y equals on your graphing calculator. If you're using the TI-84 or anything similar to that, or however you normally graph or save a function into the computer, go ahead and type that in. After you do that, go ahead and graph. From there, since this is equal to 0, remember that's going to be, where does y equal 0? It's one of the, it's where the graph is crossing the x-axis. So it's one of the x-intercepts, right? Y equals 0 at the x-intercept. So you're going to do second calculate, which is the same button as trace. It's right next to the graph button on these TI calculators. And then you'll see option number 2 says 0. So pick option number 2. Now I'm not going to write this part down. You're basically going to push enter. But notice it says left bound, so you should be below the x-axis. And then hit enter. Arrow over to be above the x-axis. Hit enter. And then hit enter again if you don't want to guess. And you will see an answer pop up on your screen. And notice what the value is for x. You're going to want to get that information without rounding, because we don't round until the very end. So I've got 1.063959. Hopefully you have something very similar. So we found the value for x. That's right here, x equals a. We can go to the next step, differentiate f of x. So I need f prime of x, which is going to be 7 times 4 is 28, x to the 6th minus 2x plus 1, and then minus 5 just becomes 0. So this is my f prime, and then that was step 2. Step 3 says evaluate f prime of a. Here's where it's a little bit important to use your calculator again. Go back to y equals, or however you save a function in your calculator, and this time we're going to enter in the derivative, 28x to the 6th minus 2x plus 1. Enter that again in y equals. Once you've entered that, use second mode, or quit is how you do it, and that takes you back to the home screen. Once you're on the home screen, what we want to do is evaluate f prime of x for this a value that we have right here. Now that's not going to be any fun. We need to store that in our calculator. So in order to store that, type in this number right here. Type this long number in on your home screen. Then push the button that says STO and has an arrow. It's just above the on button. It looks like this, STO with an arrow, and then type the letter X. We're making that and push enter. So STO, X, enter. You're saving that value to be the value of X. Then the next thing that you want to do is push your VARS button, VARS. If you don't have one of these, you're looking for a function basically. So you're doing VARS, arrow over to Y VARS, and then choose number 1. And you'll see it says Y1. You want to click that, and then on your home screen you'll see Y1, just add parentheses, X, close the parentheses. So each time is an arrow. I'm basically telling you to hit enter after that. And then what did you get? Here you should actually have your answer. Let me fix my screen now that I've written all these calculator notations. Hopefully the answer that you got looks like this. F prime of, I'm going to say A, and this right here is A, okay? Equals 50.146778805. All right, now I'm going to erase all of our calculator notes. You can go back in the video if you need to find them again. And what it said in the original problem is find the answer of F inverse prime of 3 accurate to 3 decimal places. So if this is F prime of A, remember F inverse prime would be the reciprocal. So F inverse, let me redo that, make a box, of 3 prime would equal 1 over, and we only need accurate to 3 decimal places, 50.1468. That's more than enough. I can divide that out in my calculator, 1 divided by 50.1468, and I get 0.0199. I'm going to truncate that. It could round, but I'm just going to leave it like that, 0.0199. Hopefully that was helpful. The main thing is just to keep in mind that you can find the value by setting the original function equal to the value that they gave you, because if it's the X value for the inverse, it is the Y value for the original function, and then take the derivative, plug in the answer that you got, and then take the reciprocal, okay? Now here's the part where I said that the lesson gets a little bit weird. We're suddenly going to be doing something totally unrelated to inverses. This is different types of derivatives that we haven't done, and they're all different examples of natural logs, or logarithms or exponential functions. Let a be a positive real number, a cannot equal 1, and let u be a differentiable function of x. Because they're talking about like u substitution. You'll see in here like this is a u. It just means that there's an expression or a function there. So let's look at these examples. If you're getting kind of tired of doing math, you might want to just pause here and come back to finish this part, because it's a total transition to something different. We're going to come back to inverses for the last page. So feel free to pause here and come back to it if you want to take a break. This is a good breaking point. Look at each one of these. Number 1, we have the derivative with respect to x of a to the x, which means you have just a number with x or a function as the exponent, and it tells you the derivative is going to be the natural log of a times a to the x. Look at the next one. It's a to the u, which means this time u is an actual function that's bigger than just like x. And so what you're going to do is the natural log of a times a to the function that you had, plus du dx means the derivative of whatever is in the exponent. Look at number 3, the derivative of log base a to the x, of log base a of x equals 1 over the natural log of a times x. Very similarly, number 4 is you would have 1 over the natural log of a times u. Remember, u is the exponent, so far it's the same as here on number 3, but then we times the derivative of u. Let's do some examples and it'll probably come to you pretty quickly. But I do admit there's a little bit of thinking, but it's just like plugging into a formula. So let's do this first one. Y equals 3 to the x. That is very much this style. So y prime is going to be the natural log of a, which happens to be 3 in this case, times 3 to the x. You could rewrite this if you want to, 3 to the x natural log of 3, and that would be finished, okay? Then the next one, y equals 4 times 3 to the x. This time we have number 2 because that u is represented by 3x. So we're going to have y prime equals the natural log of 4, that's a, times 4 to the 3x times, what's the derivative of 3x? It's just 3. So we can simplify this out. So this could be simplified down to be 3, I guess it's not really simplifying it, it's like rewriting it in order. You can do 4 cubed because think of this, I'll change colors for a minute. 4 to the 3x is the same thing as 4 cubed to the power of x. So we're going to rewrite this as 64 to the x power because we just want to simplify that math, remind ourselves that we can. And then notice here, this would be your final answer. You're just stuck there. There's nothing else that you could simplify. I do want to point out that there's another way you could have done this. I don't know if it's easier, but I'll show you. It looks different, but you get the same thing. You could change 4 cube x to be 2 to the 6x. Why? Because 4 is 2 squared to the 3x would be 2 to the 6x. Okay? And then what would happen when we did the derivative? We would end up with, well, let me just show you the whole steps. We would do, it would equal the 2 to the 6x. You would take the natural log of 2 times 2 to the 6x times 6, because that derivative of 6x is 6. And so you have 6 natural log of 2, 64 to the x. You get the same thing. I'm just notating that to you because another teacher did it that way, and I was like, well, I wouldn't have felt that that was easier. If you do 3 times the natural log of 4, you get the exact same thing as if you do 6 times the natural log of 2. So I prefer this way in method B, but you can go back in the video and watch it again if you want to see the other method that I just showed you and erased. Now, moving on, y equals 5x squared. This is still this same type that we have here in number 2, so we're just going to do the same thing. Y prime equals the natural log of a, which happens to be 5, times the u, which is 5 to the x squared. I forgot the 5. I started to write x squared. 5, that looks like an x2, x squared, sorry, times the derivative of x squared is 2x. And so we can simplify this. We have, pausing a moment, thinking, sorry, I was thinking there's not much you can simplify. You could rewrite it in a different order if you prefer to put your other parts first and then the natural log at the end. I'm not saying that it's any better. So we can just leave that one as is. Going to the next one, this is just a little different looking, but it's the same thing. So we're going to do the 5 to the power of 3 minus x squared. We're going to do the natural log of 5 because 5 is the a value. Then we're going to do the actual function, 5 to the power of 3 minus x squared. And then the derivative of the exponent, 3 minus x squared. The derivative of 3 is 0 minus 2x. Okay, because we multiplied by 2. So we can again leave this. There's not really any simplification. Okay, now we're going to go to the next page, find the derivative to the following, keep going. We've got log 5x, log base 5 of x. You got to go back up here to look. That's this style right here. So it's 1 over the natural log of the base times the x. So in this case, y prime equals 1 over the natural log of 5 times x, which I would rewrite personally as x natural log of 5 because I like to have the x in the front. Then we look at the second one. We've got, this is like number 4 on the table. Those 1, 2, 3, 4 up here. We've got the log with a base of a times u being an actual function, the function being sine x. Okay, so looking at our formula, we've got 1 over, I don't really like how that wrote out, sorry, 1 over the natural log of the base, which is 3, times the function, which is sine x. Sine x is the u here. And then we multiply times the derivative of sine x is cosine x. Now for me, when I simplify this, my brain immediately says, wait, if I have a cosine x in the numerator and a sine x in the denominator, then I know that that's the same as cotangent. So if I wanted to, I could simplify that out as cotangent x, over natural log of x. This is not required, but if it were a multiple choice question and you were having to simplify to get the correct answer, your choice could look like this or like this, and you would want to be able to recognize either one. Cosine over sine is the same thing as cotangent. Now, C, we've got the log of x plus 3 to the x power. So on this one, same thing. We're going to have 1 over the natural log of the base. What is the base? It's a 10. Whenever they don't have it there, remember it's a 10. And then times whatever was in the log, x plus 3 to the x, times the derivative of x plus 3 to the x. So the derivative of x is 1 plus the derivative of 3 to the x. That's going to be ln of 3 times 3 to the x times 1 is the derivative of x. We can simplify this. Y prime equals 1 plus 3 to the x natural log of 3 all over. Again, I like having the natural log at the end. There's not a specific order. You guys know that products have the commutative property and the associative property. They can be all rearranged. So that's my y prime. 3 to the x, 1 plus 3 to the x times the natural log of 3 over the quantity x plus 3 to the x times the natural log of 10. Now this last one, we're going to do the same thing again. Y prime, equals 1 over, it's a log base 2, so natural log of 2, times that function that's right there, 2x plus 1 to the 1/3. I don't need to make it a negative because it's in the denominator still. Times the derivative of 2x plus 1 to the 1/3. Remember, this is the same thing as 2x plus 1 to the 1/3. So we're going to multiply that out. So it's going to be times 1/3, 2x plus 1 to the negative 2/3 times, what's the derivative of 2x plus 1? 2. So now I'm going to need to simplify this one. Y prime equals, here on top, I'm just going to have a 1 times 2. So it's just going to be 2. And then I've got natural log of 2, 2x plus 1 to the 1/3. And maybe you already see what's happening. You don't have to write out every single step for the algebra, remember? I've got 2x plus 1 to the 1/3 and 2x plus 1 to the 2/3. Well, 1/3 and 2/3 makes what? It's just 1. So what do I have left? Y prime equals 2 over the natural log of 2. Oh, I need to rewrite that. That was pretty bad right there. Sorry. Natural log of 2 times 2x plus 1. And again, I don't need to simplify that, but I can. If you wanted to, you could distribute. Oh, what did I lose? I lost my 3. I was like, there's something that I was going to say you could distribute. I lost this 3 right here. Don't lose any numbers. There's supposed to be a 3 out here. And so it would still be here, and so it's over here. 3 I could distribute to 2x plus 1 and get 6x plus 3 times the natural log of 2. I almost lost my 3. Don't lose things. Number 8. Find an equation of the tangent line of f of x equals 6x where x equals 2. So remember, finding the equation of the tangent line means find the derivative and then write the equation using the point. So we can first go ahead and notate that f of 2 equals 6 squared, which would equal 36. So we know we're going to use the point 236. And to find the derivative, 6 to the x, that's what we've been doing up here on the previous page right here, like a, y equals 3 to the x, we can use this formula. So it's going to be that y prime equals, let me use the same notation that they used. F prime of x equals the natural log of 6 times 6 to the x. And the derivative of x is 1, so I'm not going to bother writing it down, but you could. Then I can plug in the 2. What is f prime of 2? Well, what do I know? the natural log of 6 times 6 squared equals 36 natural log of 6. You can put that in your calculator and get an estimate to be 64.50334089. Again, I'm trying not to round early, right? But if I wanted to round it off for AP, I would have to put at least 64.503. Then, finally, I can write my equation. It's either going to be y equals 36 natural log of 6 times x minus 2 plus 36. Where did that come from? Remember, we're doing the equation of the tangent line. We should write that down. We always try to write it down, remember? Tangent line. Then the other option, if you can be allowed to use a estimation, it doesn't have to be an exact answer. You could write it using the value that we found, 64.503 times x minus 2 plus 36. Coming to number 9, this is sort of just a random problem, and using a calculator makes it pretty fast. A bacteria is growing according to the function W of t equals 1.3 over, can I just not read that out loud? You can see it. For t is greater than or equal to 0, where WT is the weight of the culture in ounces and t is in hours. Find the weight of the culture after 0 hours, 2 hours, 8 hours. Now I will tell you how I did this. I put this in my calculator of WT. For WT, I put y equals. I typed that whole thing in. Da 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 da. I'm not going to write it out. Being a little bit lazy here. Plus, I want our video to be shorter. So I put this into y equals for y1, and then I went back to the home screen. No, I went to the table, and I said, okay, what are my x values? 0, 2, and 8. And if you remember, on your calculator, you can do blue, the second button, window, and you can set it to let you ask the independent variable, and then go to second graph where you see the table and type in the values of 0. So W of 0 I found out is 1, and W of 2 I found out is 1.1456, and W of 8 is 1.2843. So I already very easily found those values based on the x values or t values. And then it says, what is the limit as t approaches infinity? Notice that these numbers, it looks like it went from 1 to 1.14 to 1.28. So what we're looking for is the limit as t goes to infinity of WT. So what I did is I went ahead and started asking my calculator some bigger functions, some bigger values. What if I put W of 10, W of 20, W of 30, W of 80, W of 100, and I discovered that it's very quickly going to go to 1.3, and then the answer is going to be 1.3 every single time. It does make sense if you think about it, because you've got 1.3 over 1 times a tiny number. In the bottom, it's just going to be getting closer and closer to 1.3. Basically, we have an asymptote there. So the limit is going to 1.3. That's the answer. Now, look what happens. All of a sudden, we're back to inverse functions. I didn't necessarily like the way this worksheet is set up, but it was a good review. So now we're back to what we learned, and it's actually good for your brain to learn something and then go back to it, like take a break and reverse. So that's what we're doing here. It worked out well. So number 10, inverse derivatives by tables. Use the table at the right to find each of the indicated values below. State the ordered pairs for the inverse function g inverse of x in the column provided. So right here, g is the inverse of of g, of course. G inverse is the inverse of g. So we need to switch these two values for each of these to fill in the table. We've got -1, 0, we've got -3, 2, and we've got 2, 4. So this is our values for the inverse of g. Now we can just do each of these problems here. Find f inverse of 4 prime. Okay, the f inverse of 4 prime. They don't give us f inverse, but remember f inverse of 4 prime equals 1 over f prime of f inverse of x, right? So we just need to know what we're taking the value of. Well, let's look. If we know the f inverse of 4, then that means we know f of 4, because remember the x and y trade places. So if we go to our original graph, original table, f of 4 equals 2, then that tells us that f inverse of 2 equals 4. So now I can use this information to plug in here. I'm going to do 1 over f prime of f inverse of 2 equals what? Sorry, f inverse of 4 equals 2. F inverse of 4 equals 2. F prime of 2 we can find in the table. I don't know why my brain was having trouble spitting that out. 1 over 1. Well, that was pretty easy. F inverse of 4 prime equals 1. That's our answer. It was easy, just harder for me to say out loud. G inverse of negative 3 prime. So on this one, what do we know? G inverse of negative 3 equals what? So when is it? Right here, 2. Looking at our table, it's right here. G inverse of negative 3 equals 2. That means G of 2 equals 3. We can do the same thing we did on the other problem, A, that we just did. This prime equals 1 over G prime of G inverse of negative 3. And so that means it's going to be 1 over G prime of 2, which equals what? What is G prime of 2? It's 2. Oh, I almost wrote 2 instead of 1 over 2. So the inverse of G of negative 3 prime equals 1/2. Hopefully you're getting the idea. Write the equation for the line tangent to the graph of G of negative 1 of x when x equals 2. Okay, so we've got G inverse of 2 equals what? Look at our table. G inverse when x is 2 is 4. And so we know that G inverse of x prime equals 1 over G prime of G inverse of x. See how many times I can say it? So G inverse of 2 prime equals 1 over G prime of G inverse of 2, which means 1 over G prime of 4, because we already set up here at the top that G inverse of 2 is 4. G prime of 4, go back to our table, G prime of 4 is negative 3. So I have 1 over negative 3. So what's my tangent line? Oh, I managed to erase what I was writing. My tangent line, well, I need to know the point. What is G inverse of 2? We already said it's 4. So it's going to be y equals negative 1/3 times x minus 2 plus 4. And that is my tangent line. I used this point right here. Let me highlight it. G inverse of 2 equals 4. That's my x and y value. Now the last problem, and then our video, let's see if we can finish it in under an hour. Estimate the value of G prime of 3. Use the result to explain the behavior of the graph of the function G when x equals 3. Here's the problem. We go back up to our table. G prime of 3, there is no 3. If you're looking here at our x values, there is no 3. Remember, we did this once before. We have 2 and 4, right? We know G of 2 and G of 4. So we can estimate G prime of 3 by taking the slope using G, right, at 2 and 4. So we're going to write it out here. G prime of 3 equals G of 4 minus G of 2 over 4 minus 2. Remember, we're using the difference quotient, basically what we used to call the slope formula. G of 4, we said, is 2, and G of 2 is negative 3. So 2 minus negative 3 is going to be 2 plus 3 over 4 minus 2 is 2. So we have 5 over 2 is our G prime of 3. Is there anything this tells us about the behavior of the graph? Well, we got a positive slope. So we know that the slope of the tangent line is positive. What does that tell us about the graph of G? Well, this may be new for you. It's not really new, but it might be new refreshing your memory. Since g prime of 3 is greater than 0, what does that tell us about the graph? The graph of g of x is increasing. It's an increasing function because the slope is positive. It's increasing at x equals 3 because that's the value that we had for x. Since g prime of 3 is greater than 0, the graph of g of x is increasing at x equals 3. That was kind of randomly thrown in there just to start getting us thinking ahead about a future lesson. Go ahead and do the practice assignment, and you are good to go.